CPU and memory settings do two different jobs. Requests help the scheduler place pods. Limits cap how much a container can use at runtime. A request is the amount Kubernetes reserves for scheduling. If a node cannot fit the requested CPU or memory, that node is not feasible. The scheduler is not watching the container's future CPU graph. It uses the requests declared in the pod spec and compares them with allocatable capacity. A limit is different. It is a runtime guardrail. CPU can be throttled, and memory over the limit can cause the container to be killed. CPU and memory do not behave the same. CPU over a limit is usually throttled. Memory over a limit can end with an OOM killed container. In a real pod manifest, resources are not a top-level pod field. They live under spec, containers, the container name, and then resources. Inside that block, requests and limits are separate maps. The requests block is the scheduling contract. Here, the container asks for 500 millicores of CPU and 256 megabytes of memory. The scheduler adds those requests to what is already placed on a node. The limits block is a runtime cap. A CPU limit controls how much CPU time the container can consume. A memory limit is harder. If the process goes beyond it, the container can be terminated. CPU is measured in cores, but manifests often use millicores. 1000 millicores is one CPU core. 500 millicores is half a core. A value like 0.5 CPU is also possible, but millicores are easier to compare. Memory is measured in bytes, so the suffix matters. 256 mi means megabytes. 1 gi means gigabyte. For Kubernetes manifests, mi and gi are usually clearer than raw byte values. Resources are set per container, not once for the whole pod. If the app container requests 500 mils and the sidecar requests 100 mils, the pod needs 600 mils on the same node. In YAML, that means each container entry can have its own resources block. Kubernetes does not choose a different node for the sidecar. The entire pod lands on one node, so the requests are added together. If requests are larger than what any node can provide, the pod does not get scheduled. It stays pending with events explaining the failed fit. A common pattern is setting requests lower than limits. That lets the cluster schedule based on the guaranteed request while allowing bursts up to the limit. If a container has no request, the scheduler has less information about what the workload needs. That can pack too many pods onto a node, and the real problem only appears later as runtime pressure. Requests and limits also affect the pod's quality of service class. Guaranteed pods have matching CPU and memory requests and limits for every container. Burstable pods have some requests or limits. Best effort pods have none. For the guaranteed class, every container needs CPU and memory requests and limits, and the values must match. This is useful for workloads where predictable resource reservation matters more than burst flexibility. A namespace can use a limit range to provide default requests and limits. That means a pod manifest may omit resources, but the created pod can still receive defaults during admission. ResourceQuota is another layer. It can cap the total requests and limits allowed in a namespace. If a new pod would exceed the quota, the API server rejects it before scheduling. This distinction matters while debugging. A quota failure usually happens when you create the pod. A scheduling failure happens after the pod exists, when the scheduler cannot find a feasible node. When resource scheduling fails, start with describe pod. Look at the events section. The scheduler usually tells you whether CPU, memory, node affinity, taints, or another filter blocked placement. Then inspect the node. Capacity is the raw machine size. Allocatable subtracts what Kubernetes reserves for the system. Scheduling compares pod requests against allocatable, not raw capacity. A common debugging trap is comparing kubectl-top directly with scheduling. Top shows current usage. The scheduler used the requests from the pod spec. You often need both views to understand the full story. A practical workflow is to observe usage. Choose a request that represents normal need, set a limit only when you want a real cap, deploy and watch for pending, throttling, and OOM killed events. For exam-style questions, keep the two control points separate. Requests answer, can this pod fit on a node? Limits answer, what happens if the container tries to use more after it is running? The final mental model, requests reserve placement, limits cap runtime behavior, quotas control namespace totals, and the best debugging path is to read the manifest, the pod events, and the node allocatable values together.